Hello again, and welcome back to Virtual Algebra 2 Notes with Miss Faust. It's been quite a while since I've done one of these videos, so I am excited to be back. And I thought just for something different, we're going to start with a joke today. So, just for a little chuckle for you. I know you're super excited. What kind of joke could Miss Faust come up with? Here's my joke for today. How many eggs can you put in an empty basket? 1. Then it's not empty anymore. Ha ha ha. So, that brings us to lesson 6.11.1. Our essential question today is how are rational exponents related to radicals and roots? So, question column, notes column, and let's dive right in. So, in Algebra 1, you learned some things about exponents, or maybe in middle school math. In any case, it's probably been a while since you've done anything with them, so let's just review some basic rules that fit with exponents. So the first one is anything to the power of 0 is equal to 1. And I use a here. A just stands for any variable or any number or anything that you want. If you take it to the 0 power, it's always going to equal 1. A second exponent basic is a to the power of 1 is always equal to a. Basically, if you have one copy of something, it's just equal to a. Oh, I forgot. Another basic thing, when we have exponents, we have a to the x. The a is our base. The x is called the exponent. And it is always short for repeated multiplication. So when you see a to the x, you do a times a times a over and over, a total of x times. So whatever the exponent is, you do that many copies of a over and over again, multiplied together. So back to our rules. One copy of a is just a. That's why that one works. This one's a little bit more complicated. This one's actually just an identity that mathematicians came up with. In order to solve other problems, they needed a 0 power, and the only thing that works is 1. So there's more to that, but we can have a math party sometime if you want to know. A negative exponent, so anytime you see a to the negative n, really means that you have a fraction, and that's the same as 1 over a to the power of n. And that works the other way as well. If you have 1 over a to the negative n, that's equal to a to the power of n. So basically, anytime you see a negative exponent, it just bumps. I think of it as bumping to the other part of the fraction. This one, remember, there's like a hidden over 1 down here. So we're taking this, we're bumping it to the bottom, and we're getting 1 over a to the n. This one, the 1's on top, so we take this, bump it to the top, and we get a to the n, which again, we could put over 1 if we need to, but we don't really need to. And the last one that you may or may not remember from Algebra 1 takes us into today's lesson, which is rational exponents. Rational, remember, is another word for fraction. So a to the 1 over n is the same as the nth root of a. We'll get into using all of these in a couple minutes, but I want to get all the rules out first, and then I'll show you a bunch of examples. So we've got those rules, and then we've got some rules for how to put together things with the same base. So another rule for exponents is a to the power of m times a to the power of n. So those are two different exponents. So when you see two different exponents, but the same base, you add the exponents. So just a quick example of that, 2 to the 3rd times 2 to the 4th equals 2 to the 7th. And that works for any base as long as both bases are the same. Another rule, a to the m over a to the n. Well, then we subtract the exponents. So if you had 2 to the 5th divided by 2 to the 3rd, that would equal 2 to the 2nd. You can check those out if you want on a calculator if you don't believe me, but they really do work. 2 to the 5th is 32, 2 to the 3rd is 8, 32 divided by 8 is 4, 2 to the 2nd is 4. Look at that, she can do math. Which brings us to rule 3, which is a to the m to the power of n equals a to the m times n. So Remember, this would mean you're doing a to the m over and over again n times, which is why they multiply. So if you had 2 to the 5th to the power of 3, you would do 2 to the 5 times 3, or 2 to the 15th. Now, they look simple at first, but when we start putting them all together, they get a little bit more complicated. So that's why we're going to spend some time working with these today. And today we'll also have some fractions in them at some point. Whoops, some fractions. And we'll be working with radicals and roots. So this one is going to be really important. We're going to use this one a whole bunch of times, and we're actually going to generalize that one a little bit more right now. So here is the definition of rational exponents. So when we're thinking rational, again, we think fraction. And the way that we do that is we say a to the power of m over n is equal to, gotta be careful with my colors now, the n, remember the n was on the bottom, it becomes a root, so the nth root of a to the power of m. But the order that you do those in actually doesn't matter, so you also could put the root on the inside and the m on the outside. So the m could go there, and the nth root of a could go inside there. Both of those mean exactly the same thing. Whether you take a and raise it to a power and then take the nth root, or you take the nth root of a and then raise it to a power, you're going to get the same thing when you're done. And each time you do one of these problems, you're going to want to look at the numbers you have, and that's going to help you decide what order to do them in. So for example, if we had 8 to the power of 2/3, we could either say that's the cube root of 8 squared, or we could say, and you don't have to do both, I'm just showing you all the possibilities, it's the square root of 8 cubed. No. The cube root, that still needs to be a cube, that still needs to be a square. So the cube root of 8 squared or the cube root of 8 squared. Sound the same, look different, and if we evaluate both of those, if we just go all the way and keep looking at those, this one, I'm going to run out of space, but that's okay. We'll make it work. This one would become the cube root of 64, because 8 squared is 64. But the cube root of 64, so you want what number cubed is 64. So something times itself is 64. That's equal to 4. And over here, we do this cube root of 8 first. So we're going to square the cube root of 8. Well, the cube root of 8 is 2, because 2 times 2 is 4, and 4 times 2 is 8. So if we multiply 3 2's together, we get that, and 2 squared is 4. So you can see either way you get the same thing. Which way you write it out is just going to depend on the problem that you're doing. And really what we're looking for here is we're looking to be fluent in going back and forth between these different representations and using them to simplify some more complicated exponential expressions. So let's look at some of those examples. I can't find a blue flare pen today, so that's why we're going with the non-blue one instead. Can you tell it's purple? Okay, so where were we? Examples. And in each of these examples, we're going to use some combination of those rules from the last page. So if you have room to do both these on the same page, that would be great. So example 1, 125x to the 5/3. So when we see 125x to the 5/3, we want to think about where the 3 is going to go and where the 5 is going to go. And then we want to remember that those are going to go with both the 125 and the x. So I'm going to start by writing the cube root of 125x all to the power of 5. And the reason I do that is when I saw this 125, I immediately think, okay, do I know something I can multiply 3 times to get 125? Because this 3 is on the bottom. So if I look at that, the cube root of 125, keep track of that over here, cube root of 125 is actually equal to 5. So over here, what I can do is I can replace that cube root of 125, this part gets replaced by 5, but then what I still need is I still need the cube root with the x, because I didn't take the cube root of x, I only took the cube root of 125. So I keep that there. Now I look at this 5, and the power of 5 gets distributed to both parts of this, so I need 5 to the 5th times the cube root of x to the 5th. Well, the cube root of x to the 5th I can't do anything with. I'm just going to leave that like it is. I've already converted it from a fraction into a root, which is the direction we're going here. 5 to the power of 5 is 125. 5 to the 3rd, so this was because 5 to the 3rd is 125. 5 to the 4th then is 625, and 5 to the 5th is 3,125, I think. I'm going to double check on the chart behind me on the wall. Yep, 3,125. So this becomes 3125 times the cube root of x to the 5th. And just that x gets the cube root and the 5. That's a little 3 in there and the 5. And the 3125, we can actually find that value, so we leave that value there. Example 2. And if you have any questions about that, jot them down in the margin here and then ask me in class next time. 81 to the 3 halves. So when I see 81 to the 3 halves, immediately I think of 2, which will become a square root, and 81. So I think about whether I know a square root of 81. And if I think about it, I know that's 9 because 9 squared equals 81. This stuff isn't stuff you guys have to write down. I just want you to hear the thought process I do when I decide what order I'm going to do these problems in. So I'm going to make this the square root of 81 cubed, but then that's just 9 cubed, because the square root of 81 is 9. Well, 9 cubed, 9 times 9 is 81. 81 times 9, I believe, is 729. Yes, 729. So this is just equal to 729. Now, you could put this in your calculator and it'll give you 729. That's not going to be helpful, though, when you get into problems with variables in them. And most of these are going to have variables. So I just wanted you to start to understand. And let's move on now to variables. So 625a to the 2nd to the 1/4. So this is where we have to start putting these ideas together. So the 1/4, remember, would become a 4th root of 625a squared. So when I look at that, 4th root of 625, well, I think about that. I look at my tables, which Ms. Faust gave you in class last time, or I look up here, 5 to the 4th is 625. So the 4th root of 625 is 5, but I still need that 4th root of a squared. Now at that point, if I have a squared and the 4th root of that, just again go through my thinking over here for you, really remember that's a squared to the 1/4. Well, if we use our properties of exponents, we can multiply those to get a to the 2/4. 2/4 reduces to 1/2. 1/2 means we just need the square root of a, not the 4th root. So the answer to this is just 5 times the square root of a. And I just did that over there so it wouldn't get confusing with the 5 in front. With the square root, you don't have to put the 2 there. I just put it so you know, because when you get 3rd root, 4th root, etc., you do need it. So that way we can remember to actually put it there. So a couple more examples, and then I think you guys will be good to go. Of course, we'll do more in class together next time. Now here, we're going to go from roots to exponents. Before we were going from exponents, I should say rational or fraction exponents. Before we were going from fraction exponents to roots, now we're going the other way around. So, same idea, different problems. So example 1, if I have the 6th root of 125 squared. So when I see this, if I want to get rational exponents, I know I need to take the 6 and put it into a fraction somehow. So remember, it goes on the bottom. So I make it 125 squared to the 1/6, or I usually just write 125 to the 2/6. I just take this number, the number that you're taking the root of, and that becomes the denominator. This 2 stays the same, right? I had a 2 there, so I still need the 2 there. And now I can simplify that again. So 125, 2 divided by 6 is the same as 1/3. At that point, you might say to yourself, do I know something that I can multiply 3 times to get 125? You do. It's 5. That's equal to 5. But if we're just trying to rewrite it with a rational exponent, that's all we'd need to do. So we could put a 5 there if we want. But again, this has rational exponents. Example 2. Again, we'll go straight into variables because I think these are more interesting when you have variables. So the 8th root of 3x all to the power of 3. So we look at this and we say, okay, the 3 is on the outside this time, but that doesn't matter. That still is going to be my numerator. I should write that up here. Numerator. So the 3 is going to be my numerator, and the 8 is going to become my denominator. So I take my 3x. I'm going to put it in parentheses, because if I don't put it in parentheses, I won't be showing that the 3 and the 8 apply to both of these. And I put 3/8 there. I look at that. There's not really any way to keep simplifying this. So at that point, if you wanted, I would stop here. Okay, that's fine. If you don't like the look of that, if you want to make it 3 to the 3/8 times x to the 3/8, that wouldn't be wrong. So this is also right. But you don't need to go all that way with it. If you just stop here, that's good. And I shouldn't have kept going because now you can't even read that 3. Now it doesn't look like an exponent. It's huge. Oh well, you get the idea. So again, we're taking the 8, it's becoming the denominator, the 3 becomes the numerator. If we want, we can distribute it to both parts. Third example, square root of 2a to the 6th with the 2a in parentheses. Now this one I'm going to show you 2 different methods for doing it, and you can decide which one makes more sense to you. So again, the first thing I would do is I would write in that 2. You're not going to see it in a book because the book assumes that you know it's there, but I'll write it in for you. So if we look at the 2a and the 6 and the 2 first, what we could do is we could make this 2a to the 6/2. 6 is the numerator, 2 is the denominator. Remember, that number outside becomes the denominator. Whatever other exponent you have is the numerator. Well, hopefully you look at that and you go, wait, I know what 6 divided by 2 is. 6 divided by 2 is just 3. Indeed. Now we take 2 to the 3rd and a to the 3rd. So now we just distribute that through, because 2 to the 3rd is a number that we can figure out, right? That's not complicated. So 2 to the 3rd is 2 times 2, which is 4, times 2 more, which is 8. And we get a final answer of 8 to the 3rd. The other way you could do this, and both are equally correct, which it's just a matter of personal preference, is we start out by simplifying what's inside the square root. So again, we keep the square root. We do 2 to the power of 6 times a to the power of 6. So we're distributing that 6 inside to both parts, which gives us the square root of 2 to the power of 6, which is 64. You can check it if you don't believe me. Times a to the power of 6. Well, now we can't do anything more with this, but we can break this up into the square root of 64 times the square root of a to the 6th. Square root of 64 is 8, because 8 times 8 is 64, times, remember this, whoops, needs a 2. 2 becomes the denominator, a to the 6/2. but 6 divided by 2 is still 3. So either way that you solve that problem, you get the same 8a to the third when you're done. Okay, and the difference between this one, the reason we didn't go any further here, and here we went all the way to get just a single number with no exponent, is because here there's no easy 8th root of 3. If you could find the 8th root of 3, you could keep going. Or if this number, if this had been like 16 over 8, so we ended up with 3 squared, then you'd make it 9. But we can't do that with this. Like, this doesn't simplify anymore. There's nothing else to make it any easier. So that's the difference between this problem and this problem. And figuring out when to keep going and when to stop, that's part of what you're going to learn as you practice this more and more. Like I said, what we're really looking at is we're looking at fluency in working with this stuff, so being able to go back and forth. I didn't show any examples of using the negative exponents, but we'll look at a couple of those in class, and I think you guys can figure them out probably anyway. So with that, I will stop for today. I hope that you all have a wonderful afternoon or evening or rest of your day, and I'll see you again soon. Ciao.